Hello students, welcome to my channel ISML Academy. Today we will be doing gravitation part 2. The first question, the mass of the moon is 7.34 into 10 raised to 22 kilograms and the radius is 1.74 into 10 raised to 6 meters. The value of gravitational force will be, G is given to us. Now in the answer part we are given all the units are Newton per kilogram. Okay, so first of all we write the formula of F. So F is G m, I write small m upon r square. Okay, so let capital M is the mass of the moon and small m because we are taking it down because it is Newton, the unit of force is Newton, and we can take this small m here so that it becomes F upon m, because we want the answer in that units, force per mass Newton per kilogram. So we are left with Gm upon r square. Now we just substitute the values. So what we have is F upon m is equal to G is 6.67 into 10 raised to minus 11 into mass is 7.34 into 10 raised to 22 and r is r square. Okay. So r is 1.74 into 10 raised to 6 the whole square. Now we need to have some tricks, like see 1.74, if we take the square root of 3 we get something as 1.73 something, so we can round this. So if you take the square of 1.74 you surely get something around 3, and then we can just multiply this two numbers. Okay, or let it be, if you don't want to multiply we can also simplify this. So this is 6.67, write it as it is because we will be getting 3 in the denominator which will get easily cancel out. So 3 4. Now in the numerator plus 22 minus 11, so it becomes plus 11 upon what we get in the denominator is 3 into 10 raised to 12 because we want to square it. Okay, we square of 1.74 and square of 10 raised to 6. So square of 1.75 I'm just approximating as 3 and 10 raised to 6 is 10 raised to 12. Okay, now this is much simpler. We can just get this 3 and if you divide 6.67 by 3 you will get something as 2.22, just simple multiplication, and finally if we solve it you will get it around 1.62 Newton per kilogram. Okay, so this is the answer. You can solve it by yourself. Okay, you can even solve it by without using the log table. It's quite simple calculation. So next we come to question number 2. The centripetal force acting on a satellite orbiting around the earth and the gravitational force of earth acting on the satellite both are equal to F. The net force on the satellite is. So we'll draw a diagram. I've already drawn the diagram. You can see in this diagram, this blue part, this one, this is the earth. Okay, and this one, this is the satellite. I'll just S, this is satellite and this is earth. Okay, so this satellite is orbiting in this circular orbit. Okay, it is orbiting around this path. Okay, forming a circle. For moving along a circular path, centripetal force is required, and this centripetal force is provided by the gravitational force of attraction between the satellite and the earth. So this both are equal. Okay, so and both are equal to F. So both are one and the same thing. Okay, if there is no gravitational force there is no centripetal force, and then there is no centripetal force, the satellite won't move in the circular path. So in this case what we conclude is that the net force acting on the satellite is F. Okay, which is the centripetal force and which is of course provided by the gravitational force of attraction. So in this case the answer is B, which is F. Next is question number 3. Reason of weightlessness in a satellite is. Now see, satellite is an example of freely falling body. When a satellite is orbiting around the earth, okay, so it is as good as a freely falling body. So in a free falling body, it cannot produce any action. Okay, and when there is no action, there is no reaction. One more example is like, suppose a person is jumping from a very high rise building. He won't feel his weight until he strikes the ground. So when we are on the ground, or when we are on the earth, we feel our weight because we are producing some action on the earth, on the ground, and we are getting a reaction, therefore we are feeling our weight. But in case of satellite is an example of freely falling body, and in a freely falling body, there is no action on the floor, and when there is no action, there is no reaction. So this is the reason even astronauts, they feel weightlessness when they are on the space station, or when they are on the rocket, they feel weightless. Okay, so because the reason is they do not produce any action on the floor of that particular rocket or the space station, and therefore there is no reaction. So the answer in this case is zero reaction force by satellite surface. Next we come to question number 4. The force of gravitation is repulsive, electrostatic, conservative. Number D, non-conservative. Now see, the force of gravitation is not repulsive, it is attractive, always attractive in nature, and it is not electrostatic. Now regarding conservative, gravitational force is a conservative force. Now what is the meaning of conservative force? See, if we have a point A and we have another point B, okay, so if we have a particle at point A and we do some external work and bring the particle at this point B, okay, suppose this path is 1, okay, so we do some external work in bringing a particle from A to B, and next what we do, we take the particle from A to B through another path and bring it to the same point B. So in the second case, in the second path, in the second path we bring the particle through different path and bring it to point B. So in conservative forces, the work done in case of one and work done in case of two, both are same. So work done depends only on the end points, it does not depends on the path. So this is the property of conservative force, and they are, of course, they are path independent, and they are reversible. In case of non-conservative forces, they are those forces in which the work done depends on the path and they are irreversible. So conservative forces, the example are gravitational force, electrostatic force, magnetic forces. They are example of conservative forces. And non-conservative forces, they are like frictional force is an example of a non-conservative force. So for our example, for our case, the answer is C, conservative. The next is question number 5. Two identical solid copper spheres of radius r placed in contact with each other, the gravitational attraction between them is proportional to. So we are given two spheres, this is one sphere, this is another sphere, okay, they are in contact with each other, so the radius is r, this also radius is r, okay. So then what is the attraction between them? Okay, so both are identical, means their masses are same, so F is equal to G m upon r. The distance between them is actually, because they are in contact, so the distance of the centers is 2r, r plus r is 2r, so it becomes 2r square. So this comes out to be G m square upon 4r square. Now we need to convert this mass in terms of radius. Okay, now we have this density, rho is mass upon volume, so mass is rho into V, where V is the volume. So V is, in case of solid sphere, 4 by 3 pi r cube. Okay, so we substitute this m here in the value of m, so what we get is G m square. So this entire 4 by 3, this is rho, 4 by 3 pi r cube the whole square upon 4r square. So if we open up the bracket, what we get is, so this is G rho square 4 by 3 16 by 9, then we have pi square, and r 3 to the 6, so this is 6 upon 4 r It's r square, not r cube. This is r square. Okay, this is r square. Okay, so r square. Now if we are only interested in terms of r, because the answer is in terms of r only, so here we have r raised to 6, and in the denominator we have r square. So what we get is finally r raised to 4. So this proportion, because all these things are constant, g is constant, rho is also constant, pi is also constant, so only these two things are the dependencies on r, so it is proportional to r raised to 4. So this is the answer, r raised to 4. Next is question number 6. The masses of two planets are in the ratio 1:2. Their radii are in the ratio 1:2. The acceleration due to gravity on the planets are in the ratio. So first we write the formula for g, which is the acceleration due to gravity. This is given by gm upon r square. This capital G, it is the gravitational constant, m is the mass of the planet, and r is the radius of the planet, and g is the acceleration due to gravity. So first we write g1, it is g m1 upon r1 square, and g2 is g m2 upon r2 square. So now according to the given condition, m1 upon m2 is 1/2, and r1 upon r2 is also 1/2. In both the case capital G is constant, of course. So now we take the ratio, we write g1 upon g2. g1 is capital G m1 upon r1 square, and this is g m2 upon r2 square. g gets cancelled out, and this r2 goes up, so what we have is r2 upon r1 the whole square, and here we have m1 upon m2. So here r1 upon r2 is 1/2, so r2 upon r1 is 2, and is 2 square into m1 upon m2 is 1/2, so 2 square is 4, 4 into half is 2, so what we get is 2. So finally what we have is g1 upon g2 is 2/1, which is 2:1. So this B is the answer for this case. Next we come to question number 7. If it is assumed that spinning motion of Earth increases, then the weight of a body on equator, whether it decreases, remains constant, increases, or becomes more at poles. Now regarding the Earth, when a person is on the equator, or of course any part of the Earth, two forces are acting on it. I'll just draw this diagram of Earth. So the Earth spin on its axis. So this is the spinning motion. So at the equator, at this point something, okay, this is the equator. So two forces are acting. One is the force due to gravity, which is g m upon r square. This is the force, and then one more force, because of spinning motion there is a centrifugal force which is acting on that person who is standing on this equator, or any object which is on the equator. Now this centrifugal force, it is given by m omega square r. So the net total force, okay, the total force Ft is, one is the attractive force g m upon r square, and other which is centrifugal force, which is moving that person away, or that object away, because of the motion, spinning motion. This is m omega square r. Now as the spinning motion increases, omega increases. As omega increases, this, the total force, it decreases. Okay, so as the force actually, which is the weight, okay, it decreases. So this is what happens. So when the spinning motion of Earth increases, the weight of the body on equator also decreases. It decreases. When the spinning motion increases, the weight, it decreases. Next we come to question number 9. the last question of this session. A body has a weight 90 kilograms on the Earth's surface. The mass of the moon is 1 by 9 that of Earth's mass, and its radius is half that of Earth's radius. On the moon, the weight of the body is. Now the weight of the body on Earth is given. So let me write it as WE. So this is WE is given to us, which is equal to 90 kilograms. Now if we take G, the acceleration due to gravity on Earth, let us take it as 10 meter per second square for the sake of simplicity. So we know weight is mass into G. Okay, so WE is, so mass is constant, weight changes because of G, the value of G. So value of G is different for Earth and Moon, but mass will be same for the any body. So we calculate this mass comes out to be WE is 90 and GE is 10, so mass we get it as 9. So mass is 9 kilograms. Okay, we'll be using this data afterwards. Now next thing, some more data is given to us. What is given is mass of the moon. So I just write mm, mass of the moon is 1/9 mass of the Earth, and radius of the moon is half the radius of Earth. We have the formula for G. G is gm upon r square. So first we write the value of GE. GE is, G is of course constant, then ME, the mass of the Earth, upon RE square. Then we have GM. GM would be GMM, mass of the moon, upon GM square. Next what we do, we take the ratio of GE upon GM. So GE upon GM. So what we get is G ME upon RE square upon G MM upon RM square. Capital G gets cancelled out. Capital G gets cancelled out. So what we are left is, I'll just do the calculation here. So GE upon GM. So what we get is ME upon MM, and here what we have is RM upon RE the whole square. Now ME upon MM, we are given this ratio. Okay, this ME upon MM, we have MM upon ME upon MM is would be of course 9. So this is 9. You can get this from here. Okay, MM is 1 by 9 ME. So we take the ratio, we get this, and RM upon RE is half. So this is half square. So what we get is 9 by, this is 9 by 4. So GE upon GM is 9 by 4, but GE is 10. So we calculate from here. So we get GM is 40 by 9. GM is 40 by 9. We can just calculate, just cross multiply, substitute the value of GE as 10. So 10 4s are 40, divided by 9. Now I just come to this point here. I just rub this because I don't need this now. Okay, so we had calculated M previously. So weight on moon is equal to GM into mass, but GM is given as 40 by 9 and mass is 9 kilograms. So 9 gets cancelled out and we get the weight equal to 40 kilograms. So this is the answer, 40 kilograms is the answer. So that's all for today's session, students. So please revise it carefully, do the problems by yourself, and also refer the textbooks. All the best. Thanks for watching.